So in fact, this is the summary for what we basically just discussed. So this essentially shows you how you can basically calculate the inverter sections or the coupling sections of the filters if you know the impedances for the source, which is here written as RA, and the impedance of the load, which is here given as RB, and the required G parameters, which you can calculate based on the tables we discussed last time regarding, for example, whether you have a Butterworth, a Chebyshev, a Bessel, or any other approximation that you basically choose. And again, the values are basically totally arbitrary. So as I mentioned before, one of the big advantages of this approach is that you really can scale the filter very quickly just by essentially changing the first and the last coupling sections if your impedances end up changing, which is again an amazing convenience. And one of the other things I want to note out is that when we were talking about Chebyshev polynomials and Chebyshev approximations, we said that it can happen that your last G parameter is not equal to 1 in the normalized domain. And in that case, it might have appeared a bit of a problem because you might realize, well, what if I have a 50 ohm load and I have a 50 ohm source? Now you basically force me to not have a 50 ohm load. Well, it turns out that it's not an issue because this G parameter comes here at the very end and your inverter will take care of the impedance matching. Now, if we had done it exactly the other way, if we had actually chosen to keep our shunt elements and replace the series ones, essentially we would have basically ended up with exactly the same issue, exactly the same topology. Now we still have inverters. It's more customary to call these admittance inverters, so I'm using the J values, even though as we talked before, it's one and the same thing. And the J values that you need are basically shown down there, again, based on arbitrary now capacitance values and your G elements. Now, a few other things that you should note is that it's not only the case that we want to scale the impedances. For example, the most common impedance scaling is we start from 1 ohm from the input and the output in the normalized impedance domain. We synthesize our filter in the 1 ohm domain, and then we scale to whatever impedance we actually want. Usually, that is 50 ohms. So this type of scaling essentially means that your beginning and ending impedances, they have a ratio. And that ratio is what I'm calling here n naught, n plus 1. And as we have already learned, if that happens, all we have to do is basically scale the inverter appropriately by essentially the square root of this. But in addition to this, you should also be aware that suddenly you might choose different elements. For example, you may say, well, I designed my filter and I decided to choose an L1 prime value, an L2 prime value, L3 prime value, and suddenly I just want to change these values. So very quickly you can go ahead and choose a new value simply by multiplying this with your scaling section, with your scaling number, which is the number up here. So this scaling parameter doesn't work only for the beginning and the end, it actually works for the intermediate coupling sections as well. Now, if I take this one step further, it's quite common to, as I mentioned before, to synthesize a normalized filter first and then scale. So when we normalize things, we basically do the synthesis assuming a 1 ohm impedance, and usually we also assume those arbitrary values of L and C's to be simply 1. So if that's the case, then the coupling sections or inverters actually get the values you see here, and that is true both for the J and the K. So if you go back and you look at the equations, for example, these are the equations that we discussed for J. If you choose your C to be 1, then your J in the coupling between, let's say, 1 and 2 will simply be 1 by square root G1 and G2, which is exactly what I have basically written here. Now, exactly the same thing applies for K, and for this type of normalization, we use this common name M to essentially indicate the values of the coupling sections. And in fact, now that we have all of these coupling sections, we can basically put them in a matrix form, and we have suddenly arrived to our very first, the simplest possible way of essentially visualizing our coupling matrix. So what is really a coupling matrix for a filter is a very simple matrix that basically tells you how elements of your filter are coupled to each other. So for example, the elements 1 and 2 are coupled with the coupling section M12, which is again nothing else but square root 1 over G1, G2. And this filter is passive. This filter is basically reciprocal, so you will have exactly the same thing on the other side of the matrix. Now you will also have the source coupling section to the first element, as well as the load coupling section from the last element to the load. And if you also realize you have a bunch of elements here that are essentially 0. So for example, this element here is 0, meaning that there is no coupling between the source and, let's say, the nth element. And that's reasonable because in our section, and I will explain what I'm doing here in just a minute, in our section I have coupling only between the source and the first resonator, or the first element of the filter, and the second resonator and the second element of the filter. What I just drew there is actually a very common way of writing down the topology of the filter without having to always draw inductors or capacitors or anything like this. So what I basically draw here is these circles represents L or Cs or resonators. Later on we'll see that these are resonators for bandpass or bandstop filters. While these lines here represents the couplings. For example, this is the coupling M01 from the source to the load, so to the source to the first. This is the coupling between M12. This is the coupling between M to L. So the coupling matrix actually goes hand in hand with this type of writing the filter topology, which is very quickly done, and it's a very intuitive thing. So when we say, for example, that perhaps the M02 is equal to 0, we mean that there is no coupling between the source and the second element of the filter. This coupling that I just put with dotted lines is called the cross coupling, and it can exist. It doesn't exist in a Butterworth, and it doesn't exist in a Chebyshev filter, but it can exist in more complex filters, as we will see. So here's an example of an actual coupling matrix. So if you were to synthesize a fourth order Chebyshev polynomial and use this to make a filter, you will end up with the numbers that you will see in this coupling matrix, and I encourage you to actually do this so you get a little bit of confidence of these numbers. And if you were to basically plot the transfer function that comes out of these filters, you will basically get this graph here with the S21 and the S11 plotted.